Mr. Loera. Still cannot pronounce your name properly. On what was it? Discrete
Algebraic.
optimization?
That's right. Something. Yes, exactly. All right. So welcome back. So we talk about Graeber bases. So Graeber bases are these vector directions that allow you to augment from an integer solution to a better integer solution. Or if you cannot augment, that means that you're already at the optimal solution. And I ran out of time when I was talking about, well, Graeber bases, I mentioned, are exponentially large, even in fixed dimension. So you need some lock, or you need something to allow you to compute them. And that's exactly what I want to talk about. So if you have a nice matrix, you will be able to compute Graeber bases. So, okay, so let's talk about what are the nice matrices. So the nice matrices that I'm proposing are exactly the n-fold matrices. So again, remember, so I have n copies of B on top and n copies of A going down. So these matrix, they have a nice property. If you look at the Graeber bases of, so the Graeber bases of this matrix essentially can be recovered from a smaller matrix. So you don't have to compute the Graeber bases again for this large matrix, but it's enough. At some point, there will be a constant that depends on A and B. Your original matrix is A and B, and the n-fold matrix of that size will be all you need to compute. So this theorem is a theorem actually that came from commutative algebra. So the first people that actually look at this, I would say, were Santos and Sturmfels, independently Aoki and Takemura, and then there are generalizations by Hosten and Sullivan. But this really is a theorem that came from algebra at the very beginning. And I'm not going to prove this theorem. I just want to give you a taste of how the theorem looks like. So let's consider the example of the n-fold matrix of A, 1, 1, and B is the 2 by 2 identity matrix. So you have, in this case, this is the twofold product. You have 2 copies of the identity and then 2 copies of 1, 1 going down the diagonal. So it's not difficult to convince yourself that the Graeber basis of this is just these 2 vectors. So you have the vector 1 minus 1, 1, and the negative. So these are the 2 Graeber basis elements. Now, what the theorem is saying is that for this particular choice of A and B, and again, it depends on the choice that you make at the very beginning of A and B, you don't need to do anything else because that's all you need. For example, if you want to compute the Graeber basis of the fourfold product, well, this is the Graeber basis of the fourfold product. But look at it. Compare this to that. What do you notice? So do you notice that it's just the addition of zeros, right? So there's a lot of so essentially what this theorem says is that at some point the Graeber bases will stop growing other than adding zeros. That's essentially what's happening. Okay? And so the constant g of A that tells you that's the moment you need to stop is a constant, and therefore you have a polynomial, because essentially the number of ways that you can put the zeros is you're just choosing, yeah, it's a polynomial in n, the number of copies that you need to grow the n-fold product. Okay, so that's the theorem, and yeah, so this is it clear? So what this theorem is saying? So this means that if you have an n-fold matrix, computing the Graeber basis can be done in polynomial time in this thing. All right. These are not the only ones. These are not the only matrices that have a nice structure. So the first, in fact, some of the first matrices studied came from stochastic optimization. In stochastic integer programming, so I guess when you have a 2-stage stochastic program, then the matrices have this kind of shape. You have BBB going down, and then you have some kind of a slanted diagonal. So it's very similar to the n-fold matrix or the transpose of an n-fold matrix. So these were already studied in the PhD thesis of Raymond Hemeke. More recently, there was a massive, well, a generalization of n-fold matrices to what the authors call n-fold 4-block matrices. So these are matrices where you have essentially A, B, C, D. So A is going still down the diagonal, B is going down this way, D is going this way, and then you have a copy of C. So these are fixed matrices, and you can enlarge this matrix with as many copies as you want, following the same pattern. And for all these matrices, there's now a theorem that guarantees to you that the sizes of the Graeber bases will be controlled, so that you can actually control the sizes and compute them. You don't need to compute the entire thing. So you will have a Graeber basis that has polynomial size. Okay, are you with me? So once you have this nice structure, you can allow yourself to compute very efficiently. Not switching. Okay. Okay, so I talk about this augmentation process, right? You are pivoting from one integer solution to the next, to the next, to the next, very similar to the simplex method. And that's a very natural question. So how many augmentation steps do you need to get to the optimal solution? Yeah. Well, I mean, if you remember, the augmentation method is the following. You start at a feasible solution. Say, let's talk about the integer case. So you start at an integer solution. If it is not optimal, there must be a better Graeber basis, a Graeber basis element that is going to move you to a better value. So you need to, but there might be several of them, in fact. So you have to choose possibly a multiple of that, and then you augment and you get a better value. But the question remains, so how do you choose this pair? So there might be several ways, like in the simplex method, you have pivot rules. You know, how to choose the next pivot. For example, one very popular way is you can choose the best pair essentially greedily, the one that gives you the most improvement. That would be the most improvement here. Another way you can say is, I didn't say the C represents the objective function in the linear case. You can have, if you have a linear objective function like here, you're maximizing an integer linear program. Well, you may choose the Graeber basis element that minimizes with the smallest value of this kind. Or you can have something that people call the steepest descent, where you have to choose a Graeber basis element that minimizes, but minimizes essentially the direction. You normalize this with the one norm of the vector. Okay, so you're mostly looking at the direction of the vector rather than the length of the vector. Okay, so these are, I mean, again, I want to think of the similarities with the simplex method. So how many steps are there? So very recently, this is very fresh. We started looking at these pivot rules. So in particular, I will state some results about the steepest descent, but there are other results for the other pivot rules that I mentioned. So how many augmentations are there in this case? So the first part that you can see, sorry, I should say this is joint work with Elizabeth Feinhold, Raymond Hemeke, and John Lee. So this is that the number of augmentations is going to be bounded by the size of the Graeber basis. So because it turns out that in these kinds of pivot rule, you will only use every Graeber basis element. For the steepest descent, you will only use a Graeber basis element one time and not reuse it again. So the number of augmentation steps is bounded by the size of the Graeber basis, and this is independent of B, of the right-hand side B, the objective function C, and the initial point that you chose. So that's really, really nice. Now, this is, of course, very useful when your Graeber basis is polynomially bounded, like in which case the n-fold matrices, right? In the case of the n-fold matrices, we have a nice bound on the size of the Graeber basis. Now, in general, the Graeber basis might be humongous. So can you say something when the Graeber basis is not small? So for that, so when you're optimizing with respect to just an arbitrary set of an arbitrary matrix, then the Graeber basis is still, if you use it as some kind of oracle that you improve and improve and improve, the number of steps is going to be bounded by this quantity here. So n is the number of variables. This gamma is the maximal entry on an integer feasible solution. So you're looking at the possible integer optima. So look at the maximal coordinate of the non-zero coordinate of that. So that's going to be gamma. So if you think of the integer whole of this, is the maximum coordinate of a vertex in the integer whole. And then there's this bound, capital M, that is bounding essentially the difference between the value of the current optimum solution and the minimum. Okay? So this is a very nice bound in the sense that, well, for some matrices, this actually tells you a nice polynomial bound on the number of steps you're going to need to get to the optimal solution. Now, of course, this is not a polynomial time algorithm because of, the sizes of these numbers are, well, they're not bounded on the input size. But again, so you have some nice corollary. So if the matrix is an n-fold matrix, then you can do integer linear programs and LPs, in fact, also in a strongly polynomial time. So you can solve linear programming in a strongly polynomial time for n-fold matrices. This is interesting from the point of view that linear programming, we don't know whether it's strongly polynomial time or not in general. There's a few cases where it's known to be strongly polynomial, and this is one more of them. And again, if you have some nice bounds, say m and gamma are constant, for your particular instance, then you have a nice also strongly polynomial time algorithm for those matrices. So say, for example, if your input matrix is totally unimodular and you have bounded variables by a constant. Okay? So that's one nice thing that you know about the number of steps you're going to need once you have the Graeber basis, how many times you are going to need to jump. All right? So let's go to a different set of slides. So I'm not going to have time to do everything that I promise. So I'm thinking I have to make a choice. The choice that so Tim spoke this morning about positive Stellensatz, and so I'm going to connect what Tim was speaking today with my next part. But I invite you to ask me about the central path. I apologize to my friend Etienne or all the people that want to hear about central path. Talk to me about that. I want to just kind of make the connection to the morning session. I think is important. So let's. So another way is you can buy me a beer and I tell you. So that's yeah. Okay. Yeah, so polynomial optimization, so we have been seeing that how you connect, so you have a set of polynomial constraints, and you want to objective function is polynomial, also you want to optimize that. But to me, polynomial optimization also means that when you have an optimization problem, you should look at polynomials to help you solve the problem. And I want to give you a particular instance, which is very, very telling of that. So here's the connection to this morning. So today we talk about, Tim talked about sums of squares. So there was the mention of the work of several people. I mean, Jean Lasserre, Parrillo, and Monique Laurent. So several people have worked on this idea that when you have a polynomial optimization problem, then you can approximate it by a sequence of semi-definite programs that, as we saw this morning, you're growing on the degree of the polynomial. No? And in particular, people have looked at, so Tim mentioned the case of the independent set, the clique problem, the chromatic number. So where you have, so there's a way to approximate essentially real problems where you have 0-1 varieties or 0-1 solutions, binary solutions. No? I will show an example in a moment again. So what I'm going to do today is I'm going to actually try to do something slightly more general. So there's no reason why you should use the reals. I don't believe the real numbers have any privilege. I believe in equality of fields of numbers. And so what I'm going to talk essentially is about doing polynomial optimization over fields that are not the real numbers. So in particular, the complex numbers and the finite fields. So what's going to happen in that case is that instead of having a sequence of semi-definite programming problems, you're going to have a sequence of linear algebra problems. And that has the advantage that we have studied linear algebra for many more years than semi-definite programming. So everything that I'm going to present today is a short taste of John worked with John Lee, Susan Margulis, Peter Malkin, and Shmuel. So John is here, and I understand he'll give a more detailed version maybe later. Maybe. Okay, 3 weeks from now. So stick around. So here is a problem that Tim mentioned today in the dual version. So you have a graph, the independence number, or the stable set problem, depending whether you're Hungarian or not, I guess. You have a graph, and you have an integer k, and the question is there a subset of the vertices not two adjacent of size k? A stable set is a set of vertices, not two of them adjacent. So the complement of a stable set is a clique, or a complete graph. So the question is there a stable set of size k inside your graph? So the independence number or the stability number is the size of the largest independent set on the graph, and as Tim mentioned today, the clique number or the independence number, which are the same thing, is NP hard to compute. Okay, so here's a graph of independent set. The independence number is 2. Here's the largest independent set. Now, this is a polynomial system of equations that was proposed by Lovász. Essentially, is he mentioned this theta body, Lovász theta body. So you can consider the following system of equations that has a solution if and only if there's a stable set of size k. So first of all, I'm going to use 0, 1 variables, and so that's where you're using the real numbers. You have x squared, so for every vertex you have one variable xi. So you have xi squared minus xi equals 0. And then for every edge, you have xi times xj equals 0. And then finally, you have the polynomial that the sum of the variables has to be equal to k. So that's a linear, very simple problem. No? So yeah, and again, so you can convince yourself that there's a stable set of size k if and only if the system has equations has a solution. Okay, so these are real numbers. And here's an example for this polynomial. So there's as many polynomials as edges plus vertices. But how about coloring? So you can consider the question of colorability. So you have a graph and an integer k, and you want to ask whether you can use k colors in such a way that not two are of the same color. So here's a tree coloring of the famous Petersen graph. And you can use polynomials too. So I'm going to show you some polynomials that tell you whether a graph is k colorable or not. So if you have so this set of polynomials was introduced first by Dave Bayer in his PhD thesis when he was looking at tree colorability. But you can do this for k colorability. So this time I'm going to use the complex numbers. Okay. So you have one variable for each vertex, and you have the power xi to the k minus 1 equals 0 for every vertex. So that's what this is saying, is that the colors that you're going to use to color the graph are going to be roots of unity. Okay, so you're using the roots of unity. And then for every edge, you have an edge polynomial. So the edge polynomial is just the sum of these. So you have variables xi and xj because I and j are adjacent to each other. So you have xi to the k minus 1, and then so all of these monomials are of degree k minus 1. And I'm sure you recognize that this polynomial is nothing else than this polynomial. Well, this is a rational function that you know. So that's that polynomial. This is an easier way to write this polynomial. Okay? So now the theorem is that this system of equations has a solution if and only if the graph is k colorable. You can color the vertex of the graph with k colors. Okay. So let's see. I can leave it as yes.
So your variables now are taken by the complex roots of unity.
That's correct. These are complex roots of unity right now. Okay. So that's the difference from before. Now I'm going complex, not real anymore. And let's see. For example, let's prove that every solution is a coloring. Okay, let's just prove that direction, and then you will see why this is a really cool thing. So find a solution. Okay, so each root of unity is going to be a color. So you take the second root of unity, and that's going to be red, and then the other one is blue. Okay, so now what do I want to prove? I want to prove that if you find a solution and you have two adjacent vertices, the solutions have to, the roots of unity that you put in these two vertices have to be different, right? Suppose not. Suppose not. Okay, so you have two K-short roots of unity that happen to be the same in I and J. So what happens with this equation? Well, it becomes, if the root of unity is beta, it becomes K times beta to the K minus 1, right? But that has to be equal to 0, right? But that's a contradiction with the fact that this was a K root of unity, you see? So if there is a solution, the solutions are really colors. Yeah? Everybody see that? And you can prove the other direction. I'll leave it as an exercise. In fact, the number of colorings is k factorial times the number of solutions, because you see, you need to multiply by k factorial because you can permute the roots of unity in any way you want. So here's the system for the Petersen graph. So then the question for k colorability becomes the question of finding whether this system of equations has a solution or not, right? Okay. So for that, instead of talking about the positive Stellensatz, I want to have some kind of theorem that tells me about the non-solvability over the complex numbers or over an algebraic field. So here's the Nullstellensatz, the famous Hilbert Nullstellensatz, going back to David Hilbert. So you have a system of equations F1, F2, Fs. Yes. I stated, yeah. Actually, I don't need K to be algebraically close here. I don't need K to be algebraically close, and I will not. So in this case, for example, the coefficients of my polynomials, the examples were rational numbers, right? So yeah, K is a field, and I'm asking the question: is the system of equations F1 equals 0, F2 equals 0, Fs equals 0? Does this have a solution over the algebraic closure K bar? So there's a typo there essentially. So let's call K bar the algebraic closure. For instance, if the coefficients are real, the algebraic closure will be the complex numbers. Right? It's when you have all the solutions for the equation. Okay, so what Hilbert proved is that if you have a system of equations like this with coefficients over K, then, and there is no solution, then there will be a certificate, because you will be able to find the number 1 as a linear combination of the f's, where the coefficients are polynomials with coefficients in K again. So not K bar, but K. So if you're working over the rational, so your polynomials are rational, you will find a linear combination with rational coefficients that has this expression. Okay. So that's what I call a Nullstellensatz certificate, right? And again, so I can play the game that Tim was playing, so I would like to study what the degrees of these certificates are. So I will talk about, I hope everybody sees that this is a certificate that there is no solution, because you see, if there is a solution, then 0 will be equal to 1, right? You just plug in the solution in that equation and you get a contradiction. Yeah? Everybody with me? So that's why if you find such a certificate, you are sure that there is no solution, right? Now, what is the part that is not obvious is that how do you know that if you find such a certificate, if you have no solution, you will find such a certificate? That's not trivial to prove that always you have a certificate like this. You have a life insurance. Okay, so this is a proof that there's no solution. It's a proof of, for example, if I use this with the coloring polynomials, you will prove that there's no tricoloring or there's no K coloring of the graph. So the first question is, what's the degree? What's the bound on the degree of these alphas? So people in algebraic geometry have studied this. So how big can the alphas be? So, well, if you're an algebraic geometer, there you can think of really complicated polynomials, right? I mean, algebraic geometers like to do that. And there's a bound bicolor that says that the degree of these alphas is no more than, essentially, it's bounded always by 3 to the n in some sense, because 3 is the maximum of the possible degrees of the input data. Yeah, these are the degrees of the f's. or 3, whichever is bigger, and then raised to the number of variables. So it's exponential. The degree of these alphas is exponential on the number of variables. Okay? So that's bad news. But nevertheless, let's be hopeful. Okay, let's think about it for a moment. And so let's fix the degree. So suppose that you, as I always like to say, you were a good person and Santa Claus gives you the degree. So suppose in this case, so look at this system of equations. This is an example that has no solution. You can convince yourself there's no solution of this system of equations. Takes a second. You have x1 is either 1 or is 1 or minus 1, but you see that implies a contradiction with the other one. So there's no solution here. So there must be a certificate that this system of equations has no solution. Now, let's suppose that somebody tells me that the degree of this certificate is 1. So the polynomials are degree 1 polynomials. Then I have this kind of expression where these are the coefficients are linear polynomials, and I don't know the coefficients the coefficients of the variables. But look what I can do. I can expand these in powers of x1 and x3 and x2, and I can regroup things. Yeah, so if I expand everything here and I regroup, you will see that so now this is the original polynomial, and that has to be equal to 1. So how can that possibly be? Well, it's only true if coefficient by coefficient they are equal, right? Two polynomials are equal if and only if they have the same coefficients. Okay? So that means that, for example, the coefficient of x11 is 0, which means that this equation is 0. Yeah? So you have a nice matching, and what you end up getting is a linear equations, yeah, over the rational numbers in this case, that you can actually, so that they will tell you when there's a solution, when there's a certificate, yeah. So in this case, the guess was correct. The degree of the certificate is 1, and I can solve the system and I can find the certificate that proves to you that there's no solution. Okay. Yeah. So the punchline is, if you know the degree of the certificate, then all you have to do is linear algebra. So to make analogy with what Tim was talking about this morning, in the case when you're looking at semi-definite programming and you fix the degree, well, there you have this the Gram matrix is going to come up, but with fixed degree that gives you certain number of possible monomials. Any questions so far? Or are you with me? So here is what we call NOLA, the Null-Stellensatz linear algebra algorithm. So very simple idea. You start with a system of equations, and we have a bound. Yeah, so we know that there is really a bound that is apparently very horrible, but there's a bound. And so you fix a degree and you produce a linear system of equations. And if you find a solution, bingo, you found that the graph is not recolorable. There's no solutions, right? And you're solving a system of equations over the rational numbers. Now, of course, what the worst can happen is that the degree is actually going to be 3 to the n, right? Where n is the number of vertices. So that's going to be bad for you. Okay? But you get the idea. If the degree didn't help you, well, then you increase the degree. This algorithm is guaranteed to terminate at least. Okay? It's potentially very bad, but okay? Are you with me? Yeah. Okay. So yes.
How does it compare? I mean, you could also on the basis of the ideal, right? Is that?
Yeah. I mean, I have a slide just for that at the very end, showing that Grommer basis has no chance. Okay. No chance whatsoever. I mean, in these coloring ideals, Grommer basis is going to go dust. You'll see. Okay, so this is a very simple idea, and so there are several issues here. So as I mentioned, the bound of Kolar is exponential, but it's even worse. So Kolar constructed some polynomials for which the bound is attained. So there's actually examples of polynomials for which the bound is exponential. Okay, but there is hope. Oh, okay, actually, that's another piece of bad news. If you are a believer that P is not equal to MP, then that means that there must exist, because we're working in a problem that is NP-hard, there must exist an infinite family of graphs for which the degree of these Nullstellensatz for the independence number and for the chromatic, for this K colorability, because 3 colorability is NP-hard too, they must grow. Yeah? So they must grow with the number of vertices or edges of the graph. Okay? So that's, if you believe just on that, there must be some growth on the degrees. So in 94, Lovas asked actually the question, I mean, can somebody find these graphs? Because it's kind of interesting to know who these graphs are, because then you have some kind of evidence that P is not equal to NP. It's kind of a backing up the evidence. No? And there were several computer scientists that work on this, Razborov, Beam, and Pagliazzo. They work on this. Exactly, they were studying the growth of these polynomials for propositional logic. People in computer science studied SAT problems and all these logical instances, and then they showed some growth for problems in logical instances. So, but we wanted to try it anyway and see what happens for combinatorial questions. I mean, like the graph theory questions, essentially, the questions that appear in combinatorial optimization. So I'm going to tell you now the results. So the first is that we actually can prove that you see this graph that was predicted that P not equal to NP, the sequence of graphs for which the degree of the Nullstellensatz grows, it exists, and it's essentially any graph. So what you can prove is that if you have a graph G that has a stability number alpha G, then the degree of the Nullstellensatz certificate proving that there is no stable sets of size 1 more the size alpha G plus 1 is going to have degree alpha G, so the stability number. Now the stability number of a graph grows linearly on the number of vertices. Okay. So now the other thing we found out, and this is actually another. So this is a piece of. So this answers the Lovas question for the stability number. Okay. So this answers the Lovas question for the stability number. This also shows that, in fact, the number of terms, the number of monomials that are going to appear in the coefficients, in these alpha coefficients, is going to grow exponentially. So that's the number of monomials you have. Here's an example. So this graph has a stability number 2. Yeah? That's the largest stable set, the largest independent set. And what you can see is that the coefficient here of this, see, this is one of the coefficients of the Nullstellensatz proving that there is no stable sets of size 3, has essentially one monomial for every possible stable set. So all the stable sets appear in the coefficient. So you can see 1, 2 is one stable set, 3, 4 is a stable set, and then every possible singleton is a stable set. Okay? So, and that's the problem, that in these kinds of, and this happens for every graph, in fact. So because and I show you this family of graphs. This is just this joint union of triangles. For these, the stability number grows linearly on the number of vertices. Yeah. So that shows that the lower bound is linear on the number. So the degree of the Nullstellensatz is going to grow linearly on the number of vertices in this case. Okay. And yeah, are there any questions about this? I mean, this shows that there will be, for the stability number problem, there will be a growth of this. So that you expect. Now, this is a lower bound on the degree of the Nullstellensatz. So how about upper bounds? Well, I already told you about Collar's bound, right? But these are not special. These are special ideals. These are special polynomial ideals. For example, they have a nice zero-dimensional variety. So there's a paper by Lazard. And Brownwell, I think. So these people prove a theorem that implies that for the coloring ideals and the stability ideals, actually the degree of the Nullstellensatz cannot be more. It has to be linear. It has to be actually the degree of the maximal polynomial, the maximum degree of a polynomial times the number of variables. So as a corollary, we have proved that it's actually it's a linear upper bound and a linear lower bound. So this is the best possible that you're going to have in this case, or rather the worst possible that you're going to have in this for these kinds of problems, for the stability number. Okay, but then we started looking at colorability numbers. And we couldn't prove anything. We couldn't prove anything like that. We couldn't prove anything that grows. So then John said, well, we should really try to compute some examples. No? So, I'm showing you just one example where we prove that for the complete graph, the complete graph is not tree-colorable, right? So we can prove that for that you need a degree 4 certificate in some situations, but nothing special. So the other thing that we started doing is that we said, well, all these Nullstellen sats applies not just to the complex numbers, right? Again, all fields have to be treated equally. So you can do this over a finite field. So you can have the same, for example, here's a system of polynomials that has solutions over the algebraic closure of F2 if and only if the graph is tree-colorable. Again, I remind you, so the algebraic closure of F2 is a horrible field. So you don't want to see that field find it in the streets. It's horrible. But you are doing calculations on linear algebra over F2 to test for the Nullstellen sats. Yeah. So this is the system, and again, so this is roots of unity, but now you're thinking of the roots of unity as the joint roots of unity over a field of 2 elements. And this system has a solution if and only if there's a tree-coloring of the graph. So we took several instances of graphs that are known to be non-tree-colorable, and some of them quite large. And, well, all of these graphs, first of all, a disclaimer, none of these graphs has a 4-click, okay? So it's not so obvious that if you look at these graphs that, oh, you're going to see why it's not tree-colorable. And in fact, some of them are pretty nasty graphs. Some of them are classical, like a Misiewski graph. If you have studied graph theory, you know that these graphs are not tree-colorable. But they're famous because they're graphs that are not tree-colorable that have no triangles. So these are graphs with large cycles that don't, the large girth, they call it, that are not tree-colorable. And the number of vertices grows, they're fairly large. Here is the remember, I'm solving a linear algebra system, so I need to have a system of equations. What's the last size of the matrix of this system of equations? So I have these many rows and these many columns. And the Nullstellen sats in this case was 1. And we could prove that all these graphs that you see here are not tree-colorable just in degree 1. Very, very fast. This is linear algebra. We were not using anything fancy, just a homemade implementation of Gaussian elimination. Over F2. Yeah. Over F2, yes. And here, well, I wanted to show you the next table. This is a very interesting table because these people did in 2006 a study of what people in optimization will do to find out whether a graph is k-colorable. So they will use branch and bound, essentially. So there's 2 versions of branch and bound that the one is called branch and cut, and the other one is Desatur. So these are well-known algorithms in graph coloring. And they had these particular graphs from the table that I show you. Look at this one, for example. It had 1,400 vertices and 9,000 edges. And when they ran these algorithms, they couldn't tell whether it was tree-colorable or not. So they were able to prove bounds on the chromatic number. So they said, well, it's tree-colorable or it's between 3 and 6. So those are the upper and the lower bound on the chromatic number of the graph. Using this other, they can only prove that it's between 2 and 6. But we can use this idea of the Nullstellen sats, and we were able to prove that they are not tree-colorable using just degree 1 certificate. Yeah? So when you go to finite fields, the degree of these certificates is greatly reduced. Yeah? Benjamin?
You said that for the certificate, the coefficients will lie in F2 bar.
No. The point is that when you do the certificate, they are in F2. F2 only. You're doing linear algebra over F2. The solutions will be in the algebraic closure of F2, if there are solutions.
But So the alpha, so the coefficients of
The coefficients, so yeah, unfortunately I had a typo in my slide of the Nullstellen sats, but the Nullstellen sats should be stated the following way. The coefficients are over k. Yeah, the coefficients are over a field k. In this case, k is equal to f2. Yeah. Now, if there are no solutions over the algebraic closure, then there is a certificate with coefficients over f2 over k. So that's the strongest way to state the Nullstellen sets. But if you look at the algebraic geometry books, actually, you don't find it usually stated that way. Most algebraic geometers, oh, let's take everything algebraically close. Not necessary. Okay, yeah. So this was really exciting. I mean, we got really excited. So this is essentially the fact is that when you go to finite fields, I mean, there was no chance to get anything of large degree. We have not found an infinite family of growth. We have a candidate. So we found a paper by two Japanese graph theorists who were actually interested on finding nasty graphs for colorability. So these graphs are, let's see, what is it? Near for click free. I don't remember what is. But the point is that these graphs are not recolorable for sure, and they also I think if you have, they're critical in the sense that if you add an edge, immediately a K4 appears, but they don't have a K4. I think that's the point. And these people were actually interested in testing coloring algorithms on these graphs, and they were really nasty performance for these graphs. So we gave it a try, and we think this might be the family that shows growth in the Nullstellen set. So you can see the growth here that I have. So we have one that is this over F2, and this by the way, these are the sizes of the matrix. These are the sizes of the matrix. So you can see how the linear algebra gets massive, but linear algebra you can do a lot of things, especially over finite fields. And we know that one of these graphs is at least degree 6, but we don't know what the real degree is. I mean, we don't know. So that shows you that maybe there's a chance to prove this Lova's evidence for the p not equal to p in these graphs too, but we don't have a proof of that. I think it shows you also that these methods, so it was completely nasty for a stability number, for the stable set problem, right? Because there, every graph essentially grows linearly. The Nullstellen set is going to grow linearly. But here, it's hard to find graphs that actually grow at all, right? So it's very hard. You have to construct them really cleverly. Any questions about this? Yes?
So for stability number, you had this very nice theorem, but for chromatic number, you have only examples, right?
For chromatic number, we have extraordinary computations. I wouldn't say just examples.
Okay, okay.
Let me put it in a more positive tone. Yes. Yes, that's right. Yes.
I mean, there are those graphs, like Cayley graphs coming from groups. They have some nice, some extreme properties frequently with this graph.
Yes. Okay. We have tried. So I'm so happy you asked this question, because, of course, then the method becomes massively interesting, right? Once we have all these extraordinary computation results, we said, how about graphs with symmetry, right? Cayley graphs is a great example. Well, guess what? When you have symmetry, the Nullstellen sets can be compressed. We develop methods to do. So essentially what we started doing is we use symmetry, we use structure, and then the computations go even faster. The computations go even faster. It's much easier when you have symmetry, in fact. I mean, you're helping me rather than giving me a handicap. So I think maybe John might say something about that later. So that's the latest thing. We have some new computations where some of the graphs we couldn't do that have symmetry, like the Kneser graphs. That these graphs really are highly symmetric, and we know in advance that the group of symmetries that we can deal with these kinds of things. And there's other ideas that are very similar to cutting planes that we can apply to this. And branching is also very nice here. Yes.
So how does the Nullstellen sets perform on complete graphs for computing the chromatic number?
No, I mean, the system here. First of all, if it is a complete graph, I can reduce the system using the symmetries that I tell you, and it takes no time.
Yeah, but
for any k, for k. And I can find, I can actually write a certificate for it. I don't even need to compute it.
So you say there is a low degree certificate?
Yeah. So you mean in F2, over F2 is degree 1, always. And over the complex numbers, we prove is degree 4, always.
Oh, you
That we have a theorem. For certain graphs, we actually prove that the degrees of the certificates will be 4 for the complex numbers and 1 for the finite, for F2. Yeah.
And what happens if the, for example, independence number?
Yes.
It is known that the independence number is hard to approximate even loosely, like very, very loosely.
Yeah.
What happens if your independence, here you concentrated on the independence number 3 or whatever, and what if this number grows 3, 4, 5, and so on?
I'm not sure how to use this for approximation of the independence number. But,
the impression is that if this grows even a little bit, like from 3 to 10, you want to check if the graph has independent set of size 10, for example. It might become much harder immediately because the independence number is hard to approximate.
Yeah, but the independence number I show you anyway that is going to grow with the independence number, so it's going to grow linearly. So for that problem, I have an answer. No? It will be always the Nullstellensatz proof will grow linearly, and this is the best possible, in fact, by this theorem of Lazard.
I see.
Yeah. All right. So somebody asked about Grosvenor basis. Who asked that question? You asked the question. Okay. Here is the answer for your question. So the Grosvenor bases don't compete here. So I took wheels. You know what a wheel is? It's a graph that looks like a wheel. So you have a bunch of points on a cycle. Yeah? And then you connect everybody to the center. No? So, it's very easy to prove these graphs are not... if you pick the right parity, then they will not be k-colorable, no? Not tree-colorable. So, so here you have the we took large wheels if you want, no? But then you run the Grosvenor basis, and you can see that after 1,000, for example, if you take the wheel with 1,000 nodes, that's the last time you can compute it for the Grosvenor basis. And it performs much worse in colorability. For 4 colorability, or when you let the k of the colorability grow, it's much worse, in fact. But this is so in some sense, studying the Nullstellensatz is also part of this thing. Where people in algebraic geometry have looked at the worst case complexity of the Nullstellensatz, right? It's like in computer science, people say, "Oh, what's the worst that can happen?" And that's the theorem of Lazard. But what we're saying is, question is, how often does the bad news happen, right? The same thing with the positive Stellensatz for semi-definite programming. There might be a doubly exponential bound, but does that really happen often in real life? And that's essentially the kinds of things that are very interesting. So I only have a few minutes left. I want to say that one of the things we have been trying to do too is to understand finding the coloring. So finding the coloring regards finding the solutions of these systems of equations. And of course, Grosvenor basis is a way that you can find systems of polynomial equations. But there are other methods. I think, depending on who you ask, they're called border bases. Bernard Morin has worked a lot on this, and we feel that this kind of linear algebra approach will actually be much more compatible with these polynomials. We don't have experimental results yet, but we are hoping to. We feel that there has to be linear algebra here. It's also related perhaps to Fougère's algorithm. How to apply it for these particular ideas. You have more structure, it's more sparse, and such. All right, so I'm supposed to finish a little bit early anyway, right? So I think Adam told me I should finish 5 minutes at least, right?
No, I think we're okay. I don't think we have any important announcements.
Okay. Okay, well, then we can go another hour, right? No, just kidding. Don't worry. So, okay, so that concludes this presentation. The part that I run out of time and I couldn't talk about the central path, let me tell you a little bit about it since I have 5 minutes. I can say some things. So the central path of interior point methods so you have the convex polytope, you have your objective function. So in the simplex method, you go through the boundary edge by edge. Now in the interior point methods, the way that people in optimization think about it is you, as Tim presented this morning, you have a parameter. So you have a parameter lambda, and then you have, instead of the objective function C transpose X, you're doing C transpose X plus lambda times the sum of the logarithms of the variables. Say the problem is in the primal form AX equals BX not negative. So people think about, for each lambda you have a solution, and that gives you a point, and the sequence of these points, they will trace a path here. So now most people in optimization, I mean, they think of this path not really exactly. You have this path as some kind of approximation, as a piecewise linear approximation. So you are maybe shooting a little bit above, and then you approximate this path closely. But there's one fact, first of all, that it's not difficult to convince yourself that the central path, the exact central path, is actually an algebraic curve. So there are polynomial equations that describe the central path. So let me just say that right now. So the central path is an algebraic variety. It's a real algebraic curve. And even in this primal case, so if you think about primal dual methods, I mean, there's a representation of the primal dual central path that is very obvious. That it's a quadratic equation description of the path. But already at the very early ages of interior point methods, people were asking, so Lagerias and Bayer, they were asking, so what's the equation for the primal central path, or for the dual central path? So there you had to compute something. I mean, there's no obvious answer to what the polynomials describe this curve. You see what I mean? I mean, you're describing the path exactly, not approximately, right? Yes, it's not an issue of finding a piecewise linear approximation, but you want to know exactly what the path is. So that's the results that I was going to present, joined with Bernd Sturfels and Cynthia Vincent, that talk to me about the details, but essentially we find for the primal and the dual, we find the equation. So it's essentially recovering the projection of the primal dual version, which we use linear and quadratic equations, right? We recover that. Now, I want to send a message to people. It's like, so people only think about this portion, right? But the truth is that if you're an algebraic geometer, well, the curve continues. I mean, in fact, goes everywhere. It's like it touches every single region, or feasible region of the constraints. So another question that you can ask that is closer to the computation of interior point methods is, how curvy is the graph? Can you say something about the curvature of the central path? Because I mean, there's work by many people that if you know something about the curvature, maybe you can predict how many steps, how many Newton steps are you going to take. So if your central path is crazy like this, well, you're not going to be able to take very long steps. So, but if it is kind of straight, then you can go farther, no? So the question is, what's the total curvature of the central path? But now you're asking a question about differential geometry on an algebraic curve. So there are theorems in algebraic geometry that tell you bounds for the total curvature. So that's another result that I didn't have time to present, but we have some bounds of the total curvature for the central path. So please talk to me, buy me a beer, and I can tell you all the details. Thank you for your patience.
So we have some time for questions or remarks.
This central path, it must depend on where you start somehow, right? Is it,
Yeah, so
which is the algebraic curve? Is there a whole bunch of algebraic curves?
So, okay. So the optimizers, people in optimization start when lambda is infinity, let's say. So they start at, there's a certain point, you know, that corresponds to, is right in the center of the polytope. It's called the analytic center. Yeah? And people start tracing roughly around there by piecewise linear approximating that. So that's the portion that people really care about. Yeah? Now, algebraic geometry, well, you study the Zariski closure of this. So you have to, I mean, you have the entire curve, right? The curve goes to everywhere in the projective space.
No, it can't go everywhere.
Well, okay, it goes. It's a curve. Yeah. I mean, it extends beyond just the polytope. That's what I mean.
Yeah. Okay.
Yeah. Yeah, it extends beyond the polytope, and then, in fact, you see, the polytope is defined by choosing x greater or equal than 0. But you have a freedom. If you're really looking at the algebraic geometry, this is an artificial constraint. The non-negativity here is artificial. So you can say, essentially, forget about this, and for every choice of signs, you pick a choice of signs, you're going to find a different polyhedral region, and the central path, this algebraic curve, crosses through every one of these regions. So, yeah. So I can show you a picture. Well, some question? Yes?
Okay, so it's related to this. So with this, if you look at this central path, so the formulation I am familiar with is that you use this complementary slackness.
Yeah.
Which in a sense means that you work in an extended space.
That's right.
And so what you are doing is you take this quadratic polynomials in the extended space
and projecting them
to projection on the original variable.
That's correct. That's exactly what we're doing. That's exactly what we're doing. And you know, these are more complicated equations. You're going to get the high degree equations. But here's the beautiful thing. In linear programming, the simplex method uses circuits. I mean, to do the pivots, I mean, when you're pivoting, you're moving in a circuit direction. Guess what? The equations of the central path are circuits. So there's divine justice somehow. You know, circuits are using the simplex method, well, they are also using the interior point methods, even though people didn't know this. I mean, for the primal and dual version. No, sorry, for the primal version. Or the dual version, separated. No?
Because that's the projection, right?
Because that's the projection, yeah, because that's the projection.
Another question. Do you allow me another question related on
Please.
this other topic, on this K-colorability? So there, it seems the fact that this works so beautifully has to do with this beautiful polynomial equations,
Yes.
which are really intelligent.
Yes.
So if you try to do a canonic approach, say you take an arbitrary binary integer programming problem and you apply the same approach with this polynomials x squared equals to x, you get nowhere.
That's right.
In fact, there the certificate is always exponential.
Yes.
So do you see there any chances?
Yeah, so I compare this situation to, you know, whether you have a good model of your program or not, right? So if you see that the result we have for the stability number says that these polynomials in some sense are pretty bad, no? But the colorability, yeah, is good. I hope that eventually there could be some indicator when you have a good theorem or you know, you're going to have high degree on the Nullstein sets if you model this way or another. Yeah, for example, chromatic, just for the colorability problem, you can model it in so many different ways.
I know.
And for instance, Noga Alon, who's a very smart man, I mean, he has a different model, and we have seen there that it doesn't work as nicely as our polynomial. These cute polynomials I show. These are very special in that sense.
But do you see a chance that one can really extend this? So what I really don't understand is why this nice description for the K-colorability really works so well. It's exactly this formulation, but seems.
Well, I mean, I have some. Well, so we have some recent results where so John and I essentially started thinking. So where can we find another good combinatorial problem, right? Where are they? I mean, we found colorability seems to be a very nice problem for these kinds of methods. So what is another problem? So since we both like oriented matroids, we started looking at the problem of orientability of matroids. I mean, in matroid theory, there's a lot of questions of the type, is this matroid orientable or not? Or is this matroid realizable or not? So this is something that graph theorists, people in matroid theory care for theoretical reasons. No? It turns out that there we started to see some hope. I mean, that again, the structure of the polynomial can help you get good computational results. I think this is starting to be good.
Okay. Any other questions? If not, we thank our speaker for his nice.